For today's lesson, we will be discussing about asymptotes of rational function. So let's discuss first what is asymptotes. So when you say asymptotes, this is a line that the curve approaches but does not intersect. So let's say you graph your rational functions and then we draw this line that keeps on getting closer or approaches the curve of the function, but they will not intersect at all. So again, we call it as the asymptotes. So let's say this is your curve, or this is the graph of the function, and then this line right here, which keeps on getting closer and closer to the function itself, but they will not intersect. So again, we call them as asymptotes. Now, there are different kinds of asymptotes. We have first the vertical asymptote. So it is a vertical line of the form x over a, which the curve approaches but never touches. So let's say this is your curve, or this is the graph of your function, and then this vertical line right here is what we call as the vertical asymptotes. So take note again, they will not intersect the function and the asymptote. Now, in solving for vertical asymptotes, all we have to do is to equate the denominator of the rational function to 0. So again, all we have to do is just to get the denominator and then equate it to 0 in order for us to identify the vertical asymptote. Next is we have horizontal asymptote. So it is a horizontal line of the form y equals b, which the curve approaches but never touches. So let's say this is the graph of your rational function. The horizontal line here is what we call as the horizontal asymptote. Again, this is in the form of y equals b. Now, in order for us to identify the horizontal asymptote of a rational function, we have to consider the degree of the numerator and the denominator. Again, when we say degree, this refers to the highest exponent of the expression in the numerator and also for the denominator. So take note that for the numerator, we will use n as the degree of the numerator, and we will use m as the degree of the denominator. Again, when we are trying to identify the horizontal asymptotes, we have to look at the degree of the numerator, which is denoted by n, and we also have to look at the degree of the denominator, which is denoted by m. And we have to identify the relationship that exists between the two so that we can identify the horizontal asymptote. Now, if n is less than m, the horizontal asymptote of f of x is the line y equals 0. So once you already identify the values of n and m, and you notice that n is less than m, let's say n is 1 and then m is 2, then the horizontal asymptote of the given function is already equivalent to y equals 0. Again, this will happen if n is less than m. Now, if n is equal to m, or the degree of the numerator is just equal with the degree of the denominator, the horizontal asymptote is y equals a sub n over b sub m, where a sub n is the leading coefficient of p of x and b sub m is the leading coefficient of q of x. So in short, if the degree of the numerator is just equal with the degree of the denominator, all you have to do is to just get the leading coefficient of the numerator and the denominator. So what is the leading coefficient? So this is the coefficient that contains the variable with the highest exponent. And lastly, if n is greater than m, then that means there is no horizontal asymptote. So again, to identify the horizontal asymptotes, you just have to identify first the relationship that exists between n and m, where n is the degree of the numerator and m is the degree of the denominator. And the last type of asymptote is what we call as the oblique asymptote. So it is a line of the form y equals mx plus b, which the curve approaches but never touches. So for oblique asymptote, this one is a slanted line or diagonal line. Okay, and it is in the form of y equals mx plus b. Now, how are we going to know if oblique asymptote exists? So oblique asymptotes exist in a function if the degree of the numerator, which is n, is 1 higher than the degree of the denominator m. That is, n equals m plus 1. So there's a strict condition that we have to follow in order for us to know if oblique asymptote exists. So the numerator must be 1 higher than the degree of the denominator. So it should follow n equals m plus 1. So let's say n is 5 and m is 4. So as you can see, the degree of the numerator is 1 higher than the degree of our denominator. So that is the only condition when oblique asymptote will exist. So to get the oblique asymptote, all you have to do is to divide the numerator by the denominator using synthetic division. And the oblique asymptote is the quotient with the remainder ignored and set it equal to y. Now, if you already identified that the degree of the numerator, which is n, is 1 higher than the degree of the denominator, which is m, then all you have to do is to divide the numerator by the denominator using synthetic division. And the quotient, that will be our oblique asymptote. But you still have to equal it or set it equal to y. Now, let's determine the asymptotes of the following functions. First, let's have f of x equals 5 over x plus 1. Now, let's identify the asymptotes. First is the vertical asymptote. So, for the vertical asymptote, all we have to do is to equate the denominator to 0. So the denominator is x minus 1. So this will become x minus 1 equals 0. And then just solve for x. So just move 1 on the other side. So we have x equals positive 1. So this one right here, x equals 1, is the equation of our vertical asymptote. Next, for the horizontal asymptote, we have to check first the degree of the numerator and the degree of the denominator. So by looking at our function, the numerator is 5, which is a constant function, therefore its degree is 0. And for the denominator, it is a linear function or linear expression, therefore the degree is 1. Now comparing the two, we can say that n is less than m because 0 is less than 1. So if it happens that n is less than m, therefore, our horizontal asymptote is automatically y equals 0. So therefore, our horizontal asymptote of this given function is y equals 0. And lastly, for our oblique asymptotes, so we have to check if n is equal to m plus 1. Or if we add 1 to the degree of the denominator, it will be equal to the degree of the numerator. So we know that n is 0, m is 1. So let's just substitute here. N is 0 equals 1 plus 1. So this will become 0 equals 2, which is not equal. Since it does not satisfy the condition, which is n equals m plus 1, therefore we can say that there is no oblique asymptote. So that's it. We're able to identify now the asymptote. So for our vertical asymptote, we have x equals 1. Horizontal asymptote, we have y equals 0. And for the oblique asymptotes, there is none. Now, I just want to show you the graph of the rational function as well as the asymptotes so that you can visualize. So let's have here, this one is the Desmos again. So we have here f of x equals 5 over x minus 1. So this is the graph of our rational function. Okay, now let's put here the asymptotes. First, for our vertical asymptote, we have x equals 1. So this line right here. So as you can see, our function approaches this particular value or line, but if you will zoom in, they will not intersect. Okay, and our horizontal asymptote, we have y equals 0. I hope you can see it clearly, but this one right here, this green line, that is our horizontal asymptote. So that's it. You have the graph, you have the rational functions, and then these are our asymptotes. For our next example, let's have g of x equals 4x minus 1 all over 5x plus 3. Okay, let's now identify the vertical asymptote. So for the vertical asymptote, again, we just have to get the denominator and then equate it to 0. So we have 5x plus 3 equals 0. Now solve for x for this one. So we will move 3 on the other side. So we have 5x equals negative 3, and then divide both sides by 5. This will be cancelled. Therefore, we have x equals negative 3 over 5. So this one now is our vertical asymptote. Next, let's solve for the horizontal asymptotes. So for the horizontal asymptotes, again, we have to identify or compare the degree of the numerator and our denominator. So for the degree of the numerator, as we can see, the highest exponent of the variable is 1. And for the denominator, it's also 1. Now from here, we can say that n is equal to m. Since n is equal to m, all we have to do is to identify the leading coefficient of the numerator as well as the leading coefficient of the denominator. For the numerator, we have 4x minus 1. The leading coefficient is 4 because it contains the variable with the highest exponent. And for the denominator, our leading coefficient is 5. Same reason, it contains the variable x, which contains the highest exponent or the degree of the expression. Therefore, our horizontal asymptote is y equals 4 over 5. And last, for our oblique asymptote, so we have to check n equals m plus 1. So n is 1. M is also 1 plus 1. So this is just 1 equals 2, which is not equal again. So therefore, we can say that there is no oblique asymptote. So now that we already have the values, the vertical asymptote x equals negative 3 over 5, horizontal asymptote y equals 4 over 5. Now let's try to see again the graph of this. Now for the graph of the function, so this is our rational function. G of x equals 4x minus 1 all over 5x plus 3. So this is the rational function. Then we have the vertical asymptote, which is x equals negative 3 over 5. So this blue line right here. So that's our vertical asymptote. And for our horizontal asymptote, we have y equals 4 over 5. So this again is the graph of the function with the asymptotes. Okay, so the lines will not touch our graph itself. And for our next example, let's have h of x equals x squared minus 9 all over x plus 5. So let's start with the vertical asymptotes. So for the vertical asymptote, again, you just have to equate the denominator to 0. So that will be x plus 5 equals 0, or x is equal to negative 5. So x equals negative 5 is the vertical asymptote of this given rational function. For the horizontal asymptote, so let's get now the degree of the numerator. So as you can see, the highest exponent of the variable is 2. So that will be the degree. And for the denominator, the degree is 1. Now from here, we can say that n is greater than m. Okay? Since 2 is greater than 1, therefore, we can say that there is no horizontal asymptote. Again, this happens if n is greater than m. And last, let's solve for the oblique asymptote. For the oblique asymptote, we just have to check first n equals m plus 1. So we have n is 2 equals m is 1 plus 1. So we have here 2 equals to 2. Therefore, there is now an oblique asymptote that exists. Now to do that, we have to use synthetic division and divide the numerator by the denominator. So in using synthetic division, you have to consider the values or the coefficients of the numerator and then divide it by our divisor, or the value of x here in the divisor. So for the numerator, the coefficients are for x squared, we have 1. Now since there's no term here with variable x, we just have to write 0. And then for the constant, we have negative 9. And then we will divide it by the denominator. So that is x plus 5. You equate it to 0. Therefore, x will be equal to negative 5. Please recall how to do synthetic division because you will be needing it, especially with the oblique asymptote. Okay, now let's solve this. Bring down 1. Then multiply it to negative 5. So that is negative 5 plus 0, negative 5. Then multiply to negative 5. That will give us 25. And add negative 9 to it. We will get 16. These are now the coefficient of our quotient. So we have here x, because 1 is the numerical coefficient. X minus 5. Then 16 will be for our remainder, 16 over x plus 5. Now for the oblique asymptote, what we will just get is the quotient. So we don't need the remainder. And then after getting the quotient, you have to equate it to y. So that our oblique asymptote will be y equals x minus 5. So this is now our oblique asymptote. So in this given rational function, we have vertical asymptote, which is x equals negative 5. There's no horizontal asymptote. And then the oblique asymptote is y equals x minus 5. Now for the graph of the given rational function, we have here this one. So this is the graph of our rational function. And then for the asymptotes, for the vertical, we have x equals negative 5. And then we have y equals x minus 5, which is the oblique asymptote. So there you go. So in this given rational function, we have vertical asymptote, x equals negative 5, and an oblique asymptote, y equals x minus 5. And for our last example, let's have f of x equals x squared plus 3x plus 5 all over x plus 1. So let's solve now for the vertical asymptote. So let's get the denominator, x plus 1 equated to 0. Therefore, we have x equals negative 1 as our vertical asymptote. For our horizontal asymptote, again, we have to check the degree of the numerator and the degree of the denominator. So for the numerator, the highest degree of the variable is 2. So that is our degree. And for the denominator, we have 1. So from here, we can say that n is greater than m. Because again, 2 is greater than 1. Thus, we can say that there is no horizontal asymptote. Okay? And lastly, for our oblique asymptote, so we have n equals m plus 1, or n is 2 equals m is 1 plus 1. So this is 2 equals 2. So correct. That means there is an oblique asymptote for here. So we have to use again the synthetic division and then divide the numerator by the denominator. So for the coefficients of our numerator, we have 1 for x squared. For 3x, we have 3. And then for the constant, we have 5. We don't have to add 0 because the terms are complete from lowest to highest. And then, we will divide it by negative 1. So to get negative 1, all you have to do is to equate x plus 1 to 0. Then let's perform now synthetic division. 1 times -1 is -1, plus 3 is 2, times -1 is -2, and then 3. And then let's write this one as the quotient. So x plus 2 plus 3 over x plus 1. Again, please recall how to do synthetic division so that you can identify the oblique asymptote. And then again, we're just getting the quotient. We don't need the remainder. Thus, the oblique asymptote of this given function is y equals x plus 2. So again, we have vertical asymptote, x equals -1. There's no horizontal asymptote. And for our oblique asymptote, we have y equals x plus 2. And for the graph, so let's just show it here. So this is the graph of our rational function. And then for our vertical asymptote, we have x equals -1. So as you can see, this blue line right here. And then for our oblique asymptote, we have y equals x plus 2. So this is now the graph of our rational function. And then these are the asymptotes. So we have vertical and oblique asymptote. So that's it for today. I hope you learned something about asymptotes, what are asymptotes, and how to identify them. And see you next time.